Change in variables. Quite often, the evaluation of a double or triple integral is greatly simplified by a suitable change of variables. So, suppose this is your double integral over r f of xy dx dy. Now I need to change these variables. So let the variables xy in this double integral be changed to uv by means of the relations x equal to phi uv and y equal to xi uv, right? Which means x is written in terms of u and v. So then the double integral is transformed into this integral, this double integral over new region r dash f. Now instead of x, just write phi uv because I have changed this variable x to the other form, and writing y as xi uv, and then multiply this with determinant of j, where j is Jacobian. I will tell you this later on about this, into du dv. Here for xy I am having dx dy, for uv just write du dv. Right? Now what about this j? What is this j? This j is Jacobian of transformation. This j is curly xy over curly uv, which means this is equal to the determinant of, so first derivating this x with respect to u and then derivating this x with respect to v. So curly x over curly u and curly x over curly v. Then for y, curly y over curly u and then curly y over curly v. So this j is the Jacobian of transformation from xy to uv coordinates, and r dash is the region in uv plane which corresponds to the region r in xy plane. So there are three kinds of transformations. First one is to change the Cartesian coordinates into polar coordinates, then changing the Cartesian coordinates into spherical coordinates, and then into cylindrical coordinates. So first I am going to explain changing the Cartesian coordinates xy to polar coordinates r theta, where r is the radius and theta is the angle. So for polar coordinates, writing xy in polar coordinates, we write x as r cos theta and y as r sin theta. And when you square and sum up x square plus y square, you will get r square, because when you square this you get r square cos square theta plus r square sin square theta. That will give you simply r square. Now Jacobian. Now writing the Jacobian. So the determinant of, first I am having the variable x, so curly x over curly r, right? Then curly x over curly theta. Similarly writing for y, curly y over curly r and curly y over curly theta. Now differentiating x with respect to r, you get cos theta. Differentiating x with respect to theta, getting negative r sin theta. Differentiating y with respect to r, sin theta. And differentiating y with respect to theta, you get r cos theta. And when you solve this determinant, you get r. So according to the formula, this double integral r in fxy dx dy, this is transformed into, now writing this double integral nu 1 over region r dash. For x, just write r cos theta, and for y writing r sin theta, into, then we have to multiply with determinant of j, which has the value r. So writing r, then dr d theta, because I'm having r theta, right? Dr d theta. Alright? Okay. Next one is to change the Cartesian coordinates x, y, z into spherical coordinates r, theta, phi. So for this, your x is, you just have to learn these, right? X is r sin theta cos phi, and then y is r sin theta sin phi, and z is r cos theta. So you have to learn the values x, y, z. So for spherical coordinates, I am having these values for x, y, z. So then just square them and add them, you will get r square. Then for Jacobian, the determinant is written as, first is x, so curly x over curly r, curly x over curly theta, curly x over curly phi. Similarly for y, curly y over curly r, curly y over curly theta, curly y over curly phi. Similarly for z. So when you solve this determinant, you get the value as r square sin theta for spherical coordinates. So this, now because I'm having x, y, z, so this triple integral over v. So f of x, y, z, dx, dy, dz is equal to triple integral over v dash, and writing x as all these values, r sin theta cos phi, r sin theta sin phi, and r cos theta. And the Jacobian, the value for Jacobian, the determinant is r square sin theta. So multiply with r square sin theta, and then r theta, for r theta phi, right? Dr d theta d phi. Is it okay? Alright. Third one is to change the Cartesian coordinates x, y, z to cylindrical coordinates r, phi, z. So for this, x is r cos phi, y is r sin phi, and z is simply z. So Jacobian is written as, for x, curly x over curly r, curly x over curly phi, curly x over curly z. Similarly for y and for z. Solving this, you get this Jacobian to be equal to r. And then in the formula, just writing x, y, z in terms of r phi, which is the given, which you have to remember, and then multiply with the Jacobian, that is r, into dr, d phi, dz. Is it okay? Fine? Alright. Let's take one example. Yes? Okay. The example is, evaluate this double integral 1 minus x square minus y square over 1 plus x square plus y square square root dx dy over the positive quadrant of the circle x square plus y square equal to 1. So only two variables, dx, dy. Sorry, x and y, right? So for x and y, we need to change into polar coordinates, right? So for polar coordinates, we write x as r cos theta, writing y as r sin theta, and writing x square plus y square equal to, yes, when you solve this, you get r square. Very fine. Okay. So this double integral is written, that is given to us. We need to change the variables now. So if this is your x-axis, this is your y-axis, and we know that for the region of integration R, that is, circle is given to you x square plus y square equal to 1. But when we have calculated this, we get x square plus y square equal to r square to 1. So, which implies the radius is 1. So, suppose this is your radius having the value 1, and this is your r equal to 1, and I'm making this wedge that will describe that r varies from 0 to 1. The r equal to 1, it is the distance from the origin to this point. So r is varying from 0 to 1, and this theta varying from 0 to pi by 2. Why pi by 2? Because they have asked that evaluate this double integral over positive quadrant of the circle, and quadrant is from 0 to pi by 2, this first quadrant, right? So r varies from 0 to 1 and theta varies from 0 to pi by 2. So just putting the limits now, r is from 0 to 1, theta is from 0 to pi by 2, and writing this integral in terms of now r and theta. 1 minus, can I write this as 1 minus x square plus y square, which is equal to 1 minus x square plus y square is r square, right? So this is 1 minus r square. So I'm writing here in the numerator 1 minus r square. In the denominator 1 plus r square into the Jacobian. Have we calculated the Jacobian for polar coordinates? Yes, and that Jacobian comes out to be r. Please check again. The formula for the polar coordinates is writing f in terms of r theta and multiply with r Jacobian, determinant of Jacobian. Multiply with r, then dr d theta, right? So multiplying with r and dr d theta. Is it okay? Just formula is used over here. Alright. In the next step, what I'm going to do is, I'm just multiplying and dividing 1 minus r square, so that in the numerator I get only 1 minus r square. So this is equal to 0 to pi by 2, 0 to 1, I'm multiplying with 1 minus r square and dividing with 1 minus r square into r dr d theta. So this is equal to 0 to pi by 2, 0 to 1. So this will be 1 minus r square in the numerator. In the denominator I get 1 minus r the power 4 square root. Right? Okay. So I need to solve this innermost integral first. So I'm solving this first and then putting the value back into this. So let me mark this equation as, let me mark this as 1. So from 0 to 1, 1 minus r square, square root of 1 minus r power 4, r dr. I'm solving this integral first. This is equal to, just multiply this r with numerator minus r cube. Separating this, right? Okay, so solving first one, what we can do here, putting r square equal to t, right? If I put r square equal to t, I get 2r dr equal to dt. So because I need, okay, so for here I'm having 2r dr equal to dt. So to get 2r dr, just multiply and divide with 2. So for 2r dr, I'm writing dt over square root 1 minus t square. And because when r is 0, t is 0, when r is 1, t is 1. So limits are also from 0 to 1. So this is dt over square root of 1 minus t square, right? And then the second integral, here I put 1 minus r power 4 is equal to, okay, just put r4 is equal to t, and then you get 4r cube dr is equal to dt. So to get 4r cube dr, just multiply and divide by 4. Just put this value. So this is negative 1 over 4, 0 to 1. Limits of t are also from 0 to 1. So this is dt over square root of 1 minus t. Fine. Okay. So this is equal to 1 by 2. Now integral for this is sine inverse t from 0 to 1. Taking this denominator to the numerator. So this is sine inverse 1 is pi by 2 minus 0 minus 1 over 4. Solving this integral, you get 1 minus t power 1 by 2 over 1 by 2. Limits from 0 to 1. So this is pi by 4 minus, this is putting the value 1, you get 0, minus put 0, you get 1. So this is pi by 4 minus 1 by 2. Now putting this value of this integral in 1. So from 1 we get d theta. So this is just your constant take this outside. Integral 0 to pi by 2 1 into d theta. And integration for 1 is theta simply. 0 to pi by 2. This is equal to pi by 4 minus 1 by 2. So this is pi by 2 minus 0. And finally, you get your answer to be pi square over 8. Just multiply pi by 2. So this is pi over 4. So this is how this double integral is solved when we need to change the variables. Thank you so much for watching this video. Do like and subscribe for latest videos. Thank you.